Alrighty, everybody. So let's start by understanding the pressure volume loop of the left ventricle during a single cardiac cycle. So on this graph, the x-axis is volume in milliliters, and the y-axis is pressure in milliliters of mercury. So now we're gonna focus on the blue here. So in the blue, starting at the bottom right, is where is when the mitral valve opens and the ventricle fills with blood and pressure stays low but the volume increases, and this is called ventricular filling. So when the mitral valve opens, we have ventricle filling. Next, we reach the bottom left corner, and now the mitral valve closes, the ventricle begins to contract. Both valves are shut here. So the volume doesn't change, but pressure rises sharply, and this is isovolumetric contraction as all valves are closed. So now we're up at the top left corner. Then when the pressure in the ventricle exceeds the pressure in the aortic valve opens up and blood is ejected. And that's the top left to top right segment. But um, pressure rises sharp. Oh wait, sorry. The ejection phase, volume drops, pressure peaks, and then falls. Okay. Finally, we close with the aortic valve up here and enter isovolumetric relaxation. So the top to the bottom. And pressure falls quickly and volume stays the same. So here are some other concepts for this, specifically preload, afterload, and inotropy. So preload refers to how much the ventricle fills. It's an increase in preload shifts the loop to the right. So we start with more volume. And so preload is actually going to be the red. You see how it's the same pressure, we just have more volume throughout the entire cycle. For afterload, there is the resistance the heart pumps against. So increased afterload makes it harder to eject blood. So the loop becomes taller and narrow, so there's more pressure and less volume, like less difference in volume. And so afterload is going to be the black, which is just significantly smaller, and it's a taller, more narrow. And then inotropy is the heart's contractility. An increase in inotropy makes the heart eject more forcefully, so the loop becomes wider and taller. So I have it as both, it's just a bigger loop in general. Alright, now let's talk about baroreceptor reflex, the body's short-term way to regulate blood pressure. Okay, so here I've drawn a heart with the aortic arch and the carotid sinus, and I've drawn the brain with the medulla, the brain stem, with arrows pointing towards the veins and arteries, and an arrow pointing towards the heart. So these arrows represent increased or decreased heart rate, pointing to the heart, and vasodilation or vasoconstriction, pointing to the arteries or veins. I'm going to take a little bit of time and explain this. So on the arteries, we have things called baroreceptors, which are right here and up here. Okay, so they're found on the carotid sinus and the aortic arch. These sense stretch, so when blood pressure rises, they fire more often. They send signals to the medulla and the brainstem, which then adjust the autonomic outflow. So they send They send signal to the brain. Okay. So if blood pressure is high, so we'll see on this bottom right here, if blood pressure is high, a baroreceptor firing increases. The medulla responds by increasing parasympathetic output and, and decreasing the sympathetic tone. So the heart slows down, vessels dilate, and the pressure drops. Okay, so we see right here blood pressure rises, baroreceptor firing increases, the sympathetic tone decreases, and then the parasympathetic output increases. If blood pressure is low, the baroreceptors decrease in firing, and the medulla increases sympathetic output, raising heart rate, contractility, and vasoconstriction to bring pressure back up in the heart. So this is the vasoreceptor or baroreceptor reflex. All right, so this next section is relatively easy. So let's break down mean arterial pressure, or MAP, up here. So MAP equals cardio output times total peripheral resistance up here. So, and cardio output itself equals heart rate times stroke volume. So right here I have a little heart, right here I have a little guy showing off his muscles. And then up here I have a heart with some um, veins and arteries. So let's take a look at this. Increasing our heart rate increases increasing stroke volume or increasing resistance, all will increase MAP. So the baroreceptors reflex acts on all three of these variables to stabilize MAP from moment to moment. So, for example, if we have a decrease in stroke volume and an increase in heart rate, we will have the same output for um, cardiac output. But then if we have a increase in total peripheral resistance and a normal cardio output, then we're going to have a higher MAP. Or if we have a decrease, right, and so this one's low and SV is low, we have a decrease in CO and an increase in TPR, we're going to have the same MAP. But let's say we have an increase in heart rate and an increase in stroke volume, thus making an increase in cardiac output, and then we have an increase in total peripheral resistance, then we have an increase in MAP. So it all affects everything. So every variable affects the MAP. All right. Now let's look at how fluid moves across capillaries. So at the arterial end of a capillary, hydrostatic pressure caused by the blood pushes fluid out of the capillary into interstitial space. At the same time, there is colloid osmotic pressure from plasma proteins pulling fluid in to the capillary. At the arterial end, again, the pushing force, hydrostatic, is stronger, so we get net filtration here. Okay, so fluid moves out is what that means. And then over at the venous end, hydrostatic pressure drops, osmotic pressure increases, or I guess it doesn't increase, it stays the same. And now the pulling force is stronger, so we get net reabsorption. So this balance ensures tissues get nutrients and stay hydrated without accumulating excess fluid. Right. So edema happens when this balance of capillary fluid movement is interrupted or disrupted, rather. So when the heart, so let's take a look at an example of congestive heart failure. So right here we have congestive heart failure in this stick figure. I'm not an artist, so don't judge. But when the heart can't pump blood forward efficiently, pressure builds up in the venous system. Okay, so this increases capillary hydrostatic pressure, especially within the legs. So I have it right here. What this means is that there's more fluid being pushed out than being reabsorbed. So this leads to fluid accumulation in the interstitial space, which we call edema. So right here, there's more fluid in the leg, causing it to swell and be enlarged. Um, so to summarize, the pressure volume loop shows the mechanical events of the heart during one cycle. Preload, afterload, and inotropy all affect the stroke volume. The baroreceptor reflex rapidly adjusts the heart function and vessel tone to keep MAP stable. Okay. Fluid movement across capillaries depends on a balance of hydrostatic and osmotic pressures. And when the balance is disrupted, like in heart failure, edema can result.